In this lecture, we're going to look at the shapes of molecules and polyatomic ions. By the end of this lecture, you should be able to determine the shapes of molecules and polyatomic ions from the number of electron pairs surrounding the central atom. Let's start by clearing up what we mean by the terms molecules and polyatomic ions. So, molecules are groups of atoms joined together with covalent bonds. So things like water, H2O, carbon dioxide, CO2, methane, CH4. Overall, they are neutral. Polyatomic ions, on the other hand, are similar in as much as they're groups of atoms joined together with covalent bonds, but overall the species has a charge. So things like sulfate ions, SO4 2-, nitrate, NO3-, the ammonium ion, NH4+. These are all what we mean by the term polyatomic ions. Now, throughout this lecture, sometimes I might just refer to molecules, when in fact I'm talking about molecules and polyatomic ions. Now, we did not discuss shapes of molecules much in the higher, but in National 5 we learned that molecules made up of two atoms, like hydrogen, H2, are linear in shape. You learned that methane, which is made up of 5 atoms, takes up a tetrahedral shape. And although these rules are not wrong, there are simplifications, and we're going to look at the whole idea of shapes of molecules in a lot more detail now. What is the major factor in determining the shape of the molecule is the number of electron pairs around the central atom. And the thing to remember is that the electron pairs want to be as far away from each other as possible, because they repel each other. Because one electron pair is negative, the other electron pair is negative, they repel each other and get as far away as possible. So, if you've got 2 electron pairs in your molecule, you end up with a linear molecule where the 2 electron pairs are as far away as possible, which in this case would be 180 degrees. If you had 3 electron pairs, the shape the molecule would take would be trigonal planar. And here we have our 1, 2, 3 electron pairs, all as far apart as possible, which in this case is 120 degrees apart. If we had 4 electron pairs, then we get our classic tetrahedral shape. There's 1 electron pair, 2, 3, 4. And in this case, this classic tetrahedral, the angle between the different electron pairs is 109.5 degrees. Sometimes when we're drawing this, say if it was for methane, these 3 atoms are supposed to be in the plane of the board, and then this sort of triangle getting bigger and bigger represents a bond coming out of the board towards you, and the dashed line represents a hydrogen atom going behind the board. So very often we draw it in this 3D representation. Okay, if we move on to having 5 electron pairs, we end up with this trigonal bipyramidal shape. So we've got 1, 2, 3, 4, 5 different electron pairs. So the angle between this one and this one is 90 degrees, and between the ones lying flat in the plane, they are 120 degrees apart. And finally, the last one we'll look at will be if we've got 6 electron pairs, which rather confusingly is known as an octahedral shape. So 1, 2, 3, 4, 5, 6 different electron pairs. Okay, so to summarise that, you determine the number of electron pairs around the central atom. Then once you know how many electron pairs you've got, then if there's 2 electron pairs, it's linear, 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, and 6 octahedral. So let's work through some examples to see how you would do the whole thing. So let's say you had to work out the shape of this SF6 molecule. The central atom is the sulfur. So how many electrons does sulfur donate? Well, you look at what group it's in. It's in group 6 because it's got 6 outer electrons. So we've got 6 electrons from the sulfur, and then it's formed 6 covalent bonds with 6 different fluorine atoms. And in forming each of those covalent bonds, the fluorine atom has donated 1 electron. So each fluorine atom donates 1 electron to the central arrangement around the sulfur atom. So that means they donate a total of 6 electrons. So we end up with 12 electrons. And the electrons pair up to be in 6 electron pairs. So 6 electron pairs. We've got 6 electron pairs. The electron arrangement around the sulfur atom should be octahedral. So there's a octahedral SF6 molecule. Let's do another example. So if we're asked to work out the shape of the boron hydride molecule, well, we look at the central atom boron. It's in group 3, so it's got 3 outer electrons, and then 1 electron is donated by each hydrogen atom forming a covalent bond with it, which gives us another 3, so it gives us 6 electrons, which gives us 3 electron pairs. So 3 electron pairs, we would expect the electron arrangement around the boron atom to be trigonal planar. So there's a trigonal planar arrangement of the electron pairs around the boron atom. Okay, here's another example. It's aluminium hydride. Okay, aluminium is in group 3, so it donates 3 electrons. It forms 4 bonds with hydrogen, so that's another 4 electrons. And then because the overall thing has got a negative charge, it must have another electron. So we give it 1 more electron because it's got a charge of 1 minus. So we get a total of 8 electrons, which means 4 electron pairs, which means it should be tetrahedral in shape. And there's a tetrahedral shape with aluminium, AlH4, the overall thing having a negative charge. So finally, let's do one more example. Let's look at the ammonium ion, NH4+. Well, nitrogen is in group 5, so that's got 5 outer electrons. Then we get 4, 1 from each hydrogen atom. Then the overall thing has got a charge of 1+, which means it's lost 1 electron. So we take away one electron, giving us 8 electrons, 4 electron pairs, and again we'd expect that to have a tetrahedral shape. Okay, so that's how to work out the arrangement of electron pairs around the central atom in a molecule or a polyatomic ion. So by now you should be able to determine the shapes of molecules or polyatomic ions from the number of electron pairs surrounding the central atom, taking into account whether or not those electron pairs are bonding or non-bonding electrons.